Hi, this is a Curious Guy. I am making a short video, I hope it's short, on a little fix for this vintage calculator. This is a calculator from about 1976. It's a Commodore, my camera's tipping down. It's a Commodore 899A model. Beautiful example of a calculator on a chip. I mean, everything is on that chip. If I put the light on here, you can perhaps see it with the Commodore logo. It's very simple multiplexing of the keypads, understanding what keys you pushed, and then deciding what numbers to display or with the calculations inside. There are no external resistors or capacitors. It's literally all that you see here. Now, the niggle that I have is that the 7th digit does show some ghosting, some unwanted display digits or LEDs when you push some of the buttons. If I push the 0 or the 6 or the negative memory or the sign change, because the way that those 4 buttons are tied to the same multiplexing circuit, so the input-output pins, they create the same kind of behavior. And that basically is that when you push them, the voltage from the chip to the common cathode of the display goes down a little bit, and it shouldn't. Just to kind of recap, how do these displays work? Essentially, the chip is energizing the LEDs all at the same time. So in a display like this, you have 8 separate LEDs, 7 form the digits and 1 for the decimal point, because you can have a decimal place anywhere you like. And all of the digits receive the same, if you like, turn-on voltage or positive voltage applied to each segment in sequence. So all the digits get the top bar turned on and then turned off. Then all the digits get the upper right-hand bar turned on and turned off, and so on. All the digits get the lower bar, visible in the 0 here, turned on and turned off. And it keeps cycling through these 8 on-off patterns. The reason that we don't see that, of course, is it's happening hundreds of times a second, and we basically get a persistence of vision effect to see the digits. Now, with that going on in the background, the reason that you only see one digit and not the others is because of the way the chip controls the full circuit of current flowing through the LEDs. While the anodes, the positives of these LEDs, are charged up with a voltage, right? The cathode is controlled by the chip so that when you want to display a digit in this field, it lowers the cathode in sync with the digit to be displayed and in sync with the segments available. So in this case, it would lower the cathode, and that by lowering the cathode, you create a larger voltage drop across the LEDs, and you create enough forward bias that the LEDs will glow. So roughly about 1.5 volts, I think. And it will do that lowering of this chip when the top bar is on, when the side bars are on, when the decimal point is on, when the bottom bar is on, but it will not lower the cathode when that middle bar is on through the cycling of those LEDs. So it kind of enables the display, but blanks the display when that middle bar is being displayed. And we can actually see that sampling here. If I just show you on the oscilloscope, and it's dancing around a little bit, so I can stop it. Hang on, let me just find that. There we go. You can see what I'm sampling here is the cathode for that first digit. And you can see that it's repetitive. Every 8 events, 8 pulses, there's a repeating cycle, which is the cyclical pattern of the LED anode voltage being applied. And we can see that there's a kind of a relatively modest drop. The voltage, this is about 4 volts, and that's 3 volts. It's 1 volt per segment. And we have a 4 volt cathode, and then it drops about half a volt, once, twice, 3, 4, 5, 6, 7 times, and then goes back up, switches off. The cathode goes higher, reducing the forward potential across the LEDs, and they don't glow. And then for the 7 events, it does drop and gives you enough potential voltage to display the LEDs, or illuminate the LEDs. And of course, there have to be 7 drops, 1, 2, 3, 4, 5, 7, because there are 7 things to display. There are 6 segments and a decimal place. And if we change that to a 1 in the display, you expect 3 drops. And if I just look at, if I can just pause it somehow, I'll tell you what, I'll take a single shot. Again, we have this complex pattern, but we can see roughly a cyclical pattern, okay? It's repeating everywhere. And you have high, 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 and then you have low, high, low, low. So you have 3 lows representing the cathode is dropping 3 times in sync with the LED segments required for the number 1 and a decimal place, and is staying relatively high for the remaining LED segment events. And so they don't display. So that's what's going on. Okay, with that background, I need to fix that mystery 7th display, that flashing over here. As I push a few of these buttons on the keypad, as I said, they flash. And the reason for that is the display, the common cathode at pin number 7, if I can just lower this down a bit, the common cathode at pin number 7 is dipping lower when you push those keys. It shouldn't, but it is. And of course, everything is controlled inside the chip, so what can you do? You know, I want to keep this working. I'd like to remove that event, and I guess the chip is getting old. It's 45 years old or so. Well, one way to do that, if the challenge is not the cycling of the LED anodes, but it's the drop in the voltage on the cathode when you push the button, when you mechanically, physically just kind of push the button slowly inward, on the way down, it does that drop of about 0.3 volts, which is enough to start to bleed through the visible LED. The way to fix it is, well, if the voltage is dropping at the pin, and you don't want that voltage drop, I'm going to add a pull-up resistor, and I'm going to pull up that resistor to the actual supply voltage. Now, I've tested this, and it works. I'm not exactly sure 100% why it works, but I've looked at the scope, and I've looked at the results, and it does work. So, I guess the point is that with a pull-up resistor, you're raising the general level, voltage level of that cathode, much higher than it should be. But when you need to use it, when you need to display a digit in the 7th unit, the relative, the pin knows that it should drop the voltage on the cathode, and that voltage drop is still, even with the pull-up resistor, big enough to allow the voltage, the LED to display normally as you'd expect. And if I'll try to do it here on film. So if I just, again, look at that 7th digit, you can see it's flashing there. I don't want that. So I have here a pull-up resistor, and experimentally, it is a, we perhaps can't see it on the camera here. That's probably better. It's a 6,800 ohm resistor. Nice and big, nice and juicy, very limited current coming through from the supply to the cathode here. The cathode itself sits around 4 volts. And if I just get it into position, if I can do this on camera, I need the light on to see what I'm doing. And it's pin number 5, I believe. Tell you what, let me try it this way. Maybe it's easier this way. Let me get it in there. Oh, boy. Always when you want to record something. How about that? So if I push a button, camera's in the way, push the minus sign, push the number 6, that 7th digit's now blanking. If I push a 0, it's blanking. If I push the negative, it's blanking. But if I display numbers, and I switch that off, you can see there's absolutely no issue with the display in the number 7 position. You can't tell that digit there has got this pull-up resistor. So again, the ghosting, if I push the 6s, it's not there. Push the 0, not there. Push the negative button on and off, not there. All right, the minus memory gone. And if I take that chip out and I push my 6s, you can see the flashing is back, and the 0 is back, and the negative is back, and the minus memory is back. So the pull-up resistor is the way to go. I hope that this video hasn't been terribly boring. It's maybe useful, insightful, a little bit of learning. But this is what it's all about, right? Experimenting, trying to understand how things work, maybe trying to enjoy the repair and keeping these things alive. This thing's almost as old as I am. So I'm Curious Guy. Thanks for watching. Take care. Bye-bye.